Next, we have an exciting presentation by Professor Richard Millham. He is currently an associate professor at DUT in Durban, South Africa. After 13 years of industrial experience, he switched to academia and he has worked at universities in Ghana, South Sudan, Scotland, and Bahamas. His research interests include software evolution, bioinspired algorithms, aspects of cloud computing with interaction, big data, data streaming, fog, edge analytics, aspects of Internet of Things. He is a chartered engineer from UK, and also he's a chartered engineer assessor and a senior member of IEEE. It is my pleasure to welcome Professor Richard. Over to you, sir.
Thank you very much. I'm very happy to be here. I'd like to talk today about the use of bioinspired algorithms for intelligent energy management of renewable energy resources. Sorry. Just a brief outline. We'll talk about climate change, the South African change, consumption, smart homes, and load shifting, production, the spider-prey algorithm, costing and sizing, and end off with conclusion and future work. Now, climate change, as you can see from this graph, the temperature of the Earth has increased dramatically over the past 140 years, despite a decrease in solar irradiation. In the past 151 years, the level of carbon dioxide in the atmosphere has changed from 280 to 417 parts per million. This is mostly due to the burning of fossil fuels. So you have an increase in surface temperature, which creates increased rates of water evaporation, which again further hold heats, leading back to feedback loops, okay, melting of glaciers, more frequent flooding, more frequent hurricanes, as we might see in the Caribbean, and more frequent and destructive weather patterns such as I have mentioned, including droughts. Now, the South African case against fossil fuels. Well, we have climate change. The average rainfall per square kilometer in South Africa is less than Egypt. With decreasing rainfall, we are experiencing, regional droughts with effect on food production and availability of potable water. And we have seen this in the Western Cape, we've seen it in the Eastern Cape, and a bit in Gauteng as well. Burning of fossil fuels is no longer feasible. Traditionally, most of South African power came from coal-fired power plants. But due to the instability of the main grid and many isolated communities that are not connected to the main grid, the private or community interest in renewable energy to replace the state-owned power supply are becoming more predominant and becoming more and more needed. Now, renewable energy. One possible solution to reduce the effects of climate change is the widespread adoption of renewable energy resources, solar, wind, geothermal, biomass, etc., to replace traditional fossil fuel-based sources and usage. Now, this energy, like all other energy sources, has two sides. Consumption, where energy is utilized either autonomically or based on user preferences, or production, where the energy is produced and stored until it's consumed. Now, there's a need to balance supply and demand in order to prevent over and underloading. Although much effort has gone into renewable energy engineering, there's also a need for intelligent energy management through software. So here's an example of an energy management system. Okay, so we have traditional production sources, nuclear, coal, we have renewable energy sources, wind, geothermal, okay. We have the consumption side in terms of application, smart homes, smart grid, okay. And in the middle, of course, we have the intelligent energy management system, which is managed by various algorithms. They could be evolutionary, computational, such as genetic, or my particular area, swarm intelligence, and colony, particle swarm, artificial bee, etc. So we use these algorithms to balance off multiple optimization objectives. The main one, of course, is to meet energy demand, but also reduce operation costs, reduce emissions. So this is smart homes, very simplified. Now, smart homes obviously will consist of IoT-enabled devices that communicate and collaborate with each other as agents in order to optimize energy usage and prolong network life. Now, these devices often have different energy requirements and consumption periods. Okay, so here we have a home smart energy framework. So it consists of two aspects: appliances such as lighting or PC, which are dependent on user preferences in the room and cannot be switched off. These will be referred to as non-scheduled. Appliances such as a washing machine, which can be switched on or off as a load shifting mechanism when the power consumption exceeds a certain threshold. Now, often regions will have peak consumption times with peak energy costs and require excess production capacity to meet these demands during these particular times only. In South Africa, these times are from the hours of 6 to 9 and 18 to 21 hours. Now, what is and why should we use bioinspired algorithms? Well, bioinspired algorithms are modeled on the interesting behavior of select animals whose behaviors has been optimized over thousands of years. Now, energy management is in itself a multi-objective problem. Now, bioinspired algorithms have the ability to jump out of a local minima, the best solution for a particular objective, and search for the global minimum, the best solution for all the needed objectives. Now, due to the distributed cooperative nature of swarm-based bioinspired algorithms, these algorithms are able to process data from heterogeneous environments, which are typically found in a home. Okay, you can apply randomization and utilize efficient global and local searches to achieve a new solution, and form basic rules that form some sort of intelligence by providing an optimization to adjust for varying energy needs. Now, appliances in a smart home. This is, again, very simplified. So the connected appliances would send a request message to all appliances that are operating to obtain information on their energy and their time usage. Now, a reply message is processed if the request satisfies two conditions. The end time of the appliance sending the request has to be smaller than the appliance receiving it in order to enable proper sequencing. The total power consumption of appliance at a given time slot T does not exceed the threshold. Now, the bioinspired algorithm is executed to determine the best time for the operation of the appliance in terms of start and end times. And here's an example. Okay, so we have the fridge and freezer, okay, which is always on. Lighting is non-scheduled because it depends on the consumer. But we have things like washing machine, which consumes a lot of energy and which operates for a long period. Now, that could, if you will, be shifted or rescheduled to a different time, but just out of habit, they're often operated on, or they're operated during the peak times. So here's an example of load balancing. The figure shows the energy demand versus attempts to balance the load. The goal is to reduce usage during the peak hours by shifting the load from peak to off-peak hours. Now, from the previous slide, high energy consuming appliances like washers can be scheduled to off-peak hours without any real inconvenience to the consumers. And from this graph, of course, you can see that the threshold is not exceeded, and the total, if you will, the power consumption is evened out. Now, new bioinspired algorithm for a smart energy management on the production side. We've developed the spider prey algorithm, which imitates the behavior of spiders traversing their web to find the best and nearest prey trapped in their web. Now, unlike the social spider algorithm, not all spiders respond. Only those spiders nearby respond to trap prey, giving parallelization to tracing. Now, the trap prey will send an amplitude signal down the web as they try to escape. The degree of amplitude can indicate the freshness of prey as the prey gradually weakens from exhaustion. Now, let's apply it to a smart energy management system. The prey represents an energy source. The degree of the prey's amplitude indicates its strength as this type of resource. Nearby spiders communicating via their own frequencies converge on the best suited prey, the energy source, to ensure its incorporation into their available energy production. And here's an example of the spider prey algorithm and the spider web. Now, the spider web represents a social web for communication among the spiders. The prey within the web represents an energy source denoted in green. The larger the dot, the greater the intensity, and the web is an analogy to the constraints of a power grid. Now, the spiders illustrated in red, orange, and yellow indicate their convergence to the best energy source, with iterations removing less fit spiders using the optimization or fit function. So the red colors indicate the initial positions, okay, and the yellow indicate them moving in the next iteration to the best source, okay. Then less fit spiders are moved, and in the next iteration they come closer to the energy source until it is acquired. All right, so just talking about discovering energy peaks, this algorithm tries to search through the discovery space in order to locate the highest peak and then the next highest peak, which represent the best and next best, strongest source of energy, which is indicated by the intensity of their vibration. Now, each of these peaks will represent a group of related energy sources. The spider will also perform a techno-economic analysis of the grid, which can be existing or newly created, resulting in its optimization. This analysis consists of examining the renewable energy economic costs and technical data. Okay, so much of the optimization objectives in the hybrid management system that we saw previously form variables for consideration for this spider prey algorithm. As mentioned, these spiders will communicate among themselves by using their own frequencies that travel along the web. Now, we just did a simulation where the users can define the number of agents, the search space, and iterations. This gives it much more flexibility and is able to adapt much better to data than, say, some commercial sizing software such as Homer. And the graph shows a gradual convergence of spiders towards their prey. Basically, they're approaching their prey, they're finding the global solution. So therefore, the spider prey algorithm can improve the accuracy for capturing power sources, given that the spiders and prey can communicate across the web to find the optimal location. Okay, so um, in this particular example, we define the renewable production sources as solar, wind, and biomass with battery backup. Now, batteries used during the weak production times, such as no wind and sun, and as backup during the peak load times. Now, this was for Durban. In Stellenbosch, because of the mountains, they've tried wind farms, but the mountains blocked out the wind, and all the biomass has already been bought. So the use of, say, a biomass generator is no longer feasible. In parts of the Eastern Cape, you have a lot of biomass available, so that forms a much more feasible renewable energy source. Okay, so in addition to we will do optimal sizing of renewable energy production units and costing via this algorithm. So given various scenarios, solar, wind, biomass permutations, okay, optimal sizing of the production units to meet load demand has been calculated by this algorithm. Now, to meet a 25 kilowatt load, okay, it's calculated that we'll need 17 solar panels, 1 wind turbine, 2 biomass generators, and 201 batteries. Now, these batteries play a critical role in costing as they allow the renewables to meet load demand at peak times without requiring much more costly renewables to be in place only for those times. As many people know, solar panels, wind turbines, of course, will always vary in size and production. Okay. But they are also very costly. So we want, if you will, to minimize their usage, yet meet the load. Okay, and here are some of the considerations. We're looking for a loss of power supply probability. Okay, the estimated days in the year that this particular model would not be able to meet the load. In this case, it's 4 days. Okay, reliability, 7%. Of the time that the system would not be able to meet the load, considering unit failure. Net present value, okay, that would be return on investment, total emissions, and emission penalty costs. Minimize the amount of CO2 produced. So, the effects of climate change has been brought largely upon us by the burning of fossil fuels have been highlighted. Now, we presented a mitigating solution to the energy needs in terms of renewable energy, which will vary from type, from region to region, but can be found in any country. Bioinspired algorithms based on swarm intelligence can be utilized to find a potential solution to a multi-objective problem, such as smart energy management of renewable resources from both the load and production sides. Now, another aspect of this, of course, is swarm intelligence, is that you have numerous independent agents communicating with each other, so provides a natural, if you will, form for parallelization and, if you will, high performance computing, which is an area that should be explored. Now, we'll just talk briefly about future work, immediate future work in terms of this particular model. We need to use more real-time data from the sensor network rather than historical data in order to show the algorithm's robustness in a real-time environment, which may result in greater buy-in from skeptical consumers, particularly in South Africa. In our project, we did as a proof of concept, have numerous sensors that captured solar irradiation, wind speed, etc., and based on that, use that to help calculate the model along with historical data. Historical data, of course, is always very good, but there's some problems in that in terms of locale specific. Now, although different algorithms were used for the production and consumption side, the consumption used artificial B, optimization, and the production side used the newly developed spider prey algorithm. There is a need for better global coordination and collaboration for this smart energy system. And we need to scale the system onto a larger entity such as a smart building or city. Scalability is a big issue when you're managing a huge number of heterogeneous entities within a smart framework. And finally, there's need for more autonomicity, okay, where it's auto-managed by the environment rather than the user. Okay. And a couple references. Thank you, and any questions?
Professor Richard, thank you so much for sharing some insights on renewable energies. And you've touched on the appliances, how they consume energy. You spoke about load shedding. Some of our students that were participating or that are participating in the datathon, they were touching on how to solve the load shedding using data. So it would be interesting to see how they come about the solution. You also spoke about load balancing and prey algorithms. We really appreciate your time. This is just a token of appreciation. Thank you so much for your time and presentation. A round of applause for the professor. Thank you.